Close your eyes. Imagine biting into a French fry. The first thing you hear, a sharp, crisp crunch. Then, the golden crust shatters into hundreds of tiny fragments. Inside, the potato is soft, light, fluffy, almost like a cloud. Now imagine another fry. It bends instead of breaking. The crust is pale. The inside is dense. Oil drips from every bite. It's the same potato, the same ingredients, sometimes even the same kitchen. Yet the experience couldn't be more different. Why? For centuries, chefs believed the answer was simple. Better potatoes, better oil, better recipes. But modern science tells a different story. The perfect French fry isn't just cooked, it's engineered. Behind every unforgettable crunch lies an invisible battle between water, heat, pressure, starch, and time. Scientists now study French fries using microscopes, thermal cameras, high-speed cameras, acoustic sensors, even artificial intelligence. Not because fries are complicated, but because perfection is. Every second inside hot oil changes the potato forever. Tiny cells burst, water escapes as steam, starch transforms, proteins and sugars react, light reflects differently from the surface. Even the sound of the crunch can be measured. What looks like a simple side dish is actually one of the most fascinating engineering problems in food science. Today, we're not just making French fries, we're redesigning them. This is the science behind the perfect French fry. At first glance, every French fry looks almost identical. A strip of potato cooked in hot oil, sprinkled with salt. But inside, no two fries are exactly the same. Some develop an incredibly crisp shell. Others become soft before they even reach the table. The difference begins long before the first bite. It begins inside the potato itself. A potato is not a solid block. It's built from millions of tiny plant cells. Each one is filled with water, starch, sugars, and microscopic air pockets. Fresh potatoes are made up of nearly 80% water. That water is both the fry's greatest strength and its greatest enemy. Too much water, and the fry becomes soggy. Too little, and it becomes dry and brittle. The perfect French fry exists in a narrow balance between these two extremes. The outside must lose enough moisture to become crisp, while the inside keeps enough moisture to stay soft and fluffy. Achieving that balance is incredibly difficult. As the fry enters hot oil, its surface heats almost instantly. Water trapped inside the potato begins turning into steam. That steam rushes toward the surface, escaping through tiny cracks in the potato's structure. Every escaping bubble changes the fry forever. Some moisture leaves, some remains, and every second matters. This is why cooking time is so critical. A difference of just 30 seconds can transform a perfect fry into an ordinary one. But water isn't the only player in this story. Hidden inside every potato is another remarkable ingredient: starch. And that starch holds the secret to the perfect crunch. Most people think potatoes are simple. They're not. Inside every potato is an extraordinary microscopic world. Millions upon millions of plant cells packed together like tiny bricks. Inside those cells are microscopic starch granules. These granules store energy for the potato as it grows underground. For us, they determine texture. Every bite of a French fry is controlled by these tiny structures. Scientists divide potato starch into two major components, amylose and amylopectin. Think of amylopectin as a tangled tree. Its many branches help create softness, flexibility, creaminess. Amylose is different. It's made of long, mostly straight chains. Under the right conditions, these chains can align with one another, forming stronger, more ordered structures. When heated, starch granules absorb water. They swell, they soften. Eventually, some of the amylose begins leaving the granule. This process is called gelatinization. It changes everything. The potato begins losing its raw structure. Instead, it becomes tender, creamy, and ready for its next transformation. But the real magic happens later, when water leaves the surface and the starch begins to reorganize. This is where the crispy crust begins its journey. The outside of the fry slowly transforms from a soft layer of cooked potato into something much stronger, something almost glass-like. And understanding that transformation is what separates ordinary cooking from engineering. Imagine dropping two French fries into the same fryer. They spend the same amount of time in the oil. They come from the same potato. Yet one produces an unforgettable crunch, while the other turns soft within minutes. The secret isn't the oil, it's the crust. Scientists often describe the ideal French fry as having two completely different worlds: a dry, rigid, golden shell, wrapped around a soft, moist, cloud-like center. Creating that contrast is one of the greatest challenges in food science, because the crust doesn't simply appear, it must be built. As heat travels into the potato, water near the surface begins to evaporate. Steam escapes through tiny openings between plant cells. Each escaping droplet leaves behind a little more empty space. Slowly, the outer layer becomes drier, harder, more fragile. Meanwhile, something remarkable happens inside the starch. Earlier, during gelatinization, some amylose molecules escaped from the swollen starch granules. Now, as water disappears, those long molecular chains begin moving closer together. They align, they reconnect, and they form a stronger network. Think of pouring wet concrete. At first, it's soft and flexible, but as the water disappears, the concrete hardens. Amylose behaves in a surprisingly similar way. As moisture leaves, it creates a rigid framework throughout the fry's surface. This thin outer shell is what gives the fry its famous crunch. Scientists sometimes compare this layer to glass, not because it's transparent, but because it fractures in a similar way. When you bite into a perfect fry, the crust doesn't bend, it breaks. Thousands of microscopic cracks spread across its surface in an instant. Your ears hear those tiny fractures. Your brain recognizes them as freshness, and your mouth experiences what we simply call crunch. But achieving this delicate structure isn't easy. Remove too much water, the crust becomes hard and dry. Leave too much water, it becomes soft and chewy. The perfect French fry exists within an incredibly narrow window, and researchers are constantly searching for ways to make that window easier to reach. One of the most surprising methods doesn't involve heat at all. It involves sound. Imagine placing a potato inside a tank of water. Now imagine powerful sound waves passing through that water, 40,000 times every second. The potato barely moves. You hear almost nothing. Yet beneath the surface, millions of invisible explosions are taking place. This is ultrasound. Unlike the sounds we hear every day, ultrasonic waves vibrate at frequencies beyond human hearing. When these waves travel through liquid, they create microscopic bubbles. These bubbles rapidly grow, then collapse. Scientists call this phenomenon cavitation. Although each bubble is incredibly small, its collapse releases tiny bursts of energy. Millions of these microscopic events occur every second. Together, they gently reshape the potato's surface. Researchers have found that ultrasonic treatment can create microscopic channels and tiny fissures within plant tissues. These pathways allow water to move more easily during later stages of cooking. In other words, the potato becomes better prepared for dehydration. Not by cutting it, not by piercing it, but by using sound. Imagine opening thousands of tiny escape routes for moisture. When the potato later enters hot oil, steam finds those pathways. Water escapes more efficiently. The crust develops more evenly. Some studies have reported improvements in crispness and reduced frying time after ultrasonic pre-treatment. Although the exact results depend on factors such as potato variety, treatment conditions, and cooking method. It's an extraordinary idea. Instead of changing the recipe, scientists are changing the potato itself, using nothing more than vibrations. This isn't common in everyday kitchens, but in research laboratories, ultrasound is becoming an exciting tool for improving texture while reducing cooking time and oil absorption. It's another reminder that the future of cooking may depend as much on physics as it does on recipes. If crispness has a greatest enemy, it's water. Fresh potatoes are filled with it. Every cell contains it. Every bite depends on it. Yet, to build the perfect crust, much of that water must disappear. Not all at once, and not from every part of the potato. Only from the right places at exactly the right time. This is why many chefs refuse to fry potatoes only once. Instead, they cook them in stages. The first cook is gentle. Its purpose isn't to create color or crunch. It's to prepare the potato. Inside, the starch finishes gelatinizing. The cells soften. Moisture begins moving toward the surface. Then something unexpected happens. The fries are removed from the oil and allowed to cool. Sometimes they're refrigerated. Sometimes they're frozen. At first, this seems completely unnecessary. Why cool something you're about to cook again? The answer lies inside the starch. As the fries cool, the gelatinized starch begins reorganizing itself. Scientists call this process retrogradation. Amylose molecules slowly reconnect. The surface becomes firmer, stronger, more stable. Cooling also redistributes moisture. Some water continues moving from the center toward the outer layers. When the fries return to hot oil, much of that moisture escapes rapidly as steam. The strengthened surface hardens quickly. The crust forms faster. The inside remains soft. The outside becomes crisp. This simple cycle, heat, cool, heat again, has transformed the way many of the world's best chefs prepare French fries. It isn't just tradition, it's science. And before the final fry begins, everything is now ready for the most dramatic transformation of all. The moment when pale potato becomes brilliant gold. Everything has led to this moment. The potato has been selected, prepared, cooked, cooled. Its starch has transformed. Its moisture has shifted. Now it faces the final test, the second fry. This is where chemistry, physics, and engineering work together in just a few minutes. As the potato enters the hot oil, its surface temperature rises almost instantly. The oil itself may be around 180 degrees Celsius, but something fascinating happens. The inside of the fry never reaches that temperature. Instead, the water trapped inside begins turning into steam. As long as liquid water remains, the center stays close to 100 degrees Celsius. That means the inside doesn't fry, it steams. The crispy shell protects a soft interior. This balance is what creates the perfect contrast. Outside, crunch. Inside, fluffiness. Meanwhile, the escaping steam performs another important job. It pushes outward against the crust. This pressure helps keep oil from rushing deep into the potato during the early stages of frying. As moisture escapes, the crust becomes stronger, more rigid, and more golden. But color doesn't come from the oil. It comes from chemistry, specifically the Maillard reaction. When amino acids meet natural sugars under high heat, hundreds of new flavor compounds begin forming. The surface changes. Pale yellow becomes golden brown. New aromas appear. Nutty, toasty, almost buttery. The smell we associate with freshly cooked fries is actually a cloud of newly created molecules. Scientists have identified hundreds of aroma compounds produced during this reaction. Together, they create one of the most recognizable smells in the world. Every second matters. Too little time, the crust remains weak. Too much, the sugars burn. Bitterness replaces sweetness. The perfect fry exists within a remarkably small window. A few degrees too hot or a few seconds too long can destroy everything. This is why great fries are never accidental. They are timed, measured, and controlled. Most people think crunch is a feeling. Scientists know it's also a sound. The moment your teeth break through a crispy crust, tiny fractures race across its surface. Each fracture releases a small burst of energy. Together, those tiny fractures create the sound we recognize as crunch. Researchers have spent years studying this phenomenon. Some laboratories use highly sensitive microphones to record foods as people bite into them. Others use force sensors that measure exactly how much pressure is needed to break the crust. High-speed cameras capture events too fast for the human eye. Computers analyze waveforms, decibel levels, and fracture patterns. Why? Because sound influences taste. Studies have shown that foods producing sharper, higher-frequency crunch sounds are often perceived as fresher and crispier, even when their ingredients are identical. In one sense, your ears taste food before your tongue does. Scientists also measure moisture levels, texture, oil absorption, surface roughness, even the microscopic thickness of the crust. Every measurement helps explain why one fry feels ordinary while another feels unforgettable. The perfect French fry isn't judged only by chefs. It can also be studied, measured, and improved by science. For thousands of years, cooking relied on experience. Today, it increasingly relies on data. Modern restaurants already use digital thermometers, automatic fry timers, oil quality sensors, computer-controlled fryers. But this is only the beginning. Researchers are exploring artificial intelligence that can monitor cooking in real time. Imagine cameras watching every fry, tracking color changes, steam production, surface texture. The system compares each fry against thousands of successful examples, then automatically adjusts cooking time, oil temperature, or basket movement. Not after cooking, during cooking. Food engineers are also investigating new techniques: air frying, vacuum frying, lower oil cooking, improved potato varieties, advanced freezing methods, ultrasonic processing. Each innovation seeks the same goal: more crunch, less oil, better flavor, greater consistency. The future kitchen may look very different from today's, not because potatoes have changed, but because our understanding of them has. The humble French fry has become a laboratory, a place where chemistry, physics, engineering, computer science, and culinary art all meet. Thousands of years ago, people in the Andes domesticated the potato. Centuries later, someone sliced it, dropped it into hot oil, and unknowingly began one of the greatest culinary journeys in history. Today, the perfect French fry is no longer a mystery. It is the result of countless invisible processes: water escaping as steam, starch transforming into structure, sugars creating color, proteins building flavor, heat shaping texture. Every crisp bite tells the story of physics. Every golden surface reflects chemistry. Every fluffy center reveals remarkable biological engineering hidden inside a simple potato. The next time you order French fries, take a closer look. Listen to the crunch. Watch the steam rise. Notice the contrast between the crisp shell and the soft interior. Because what seems ordinary is actually one of the most sophisticated food transformations humans have ever mastered. The perfect French fry isn't just cooked, it's engineered. And behind every unforgettable bite lies centuries of curiosity, scientific discovery, and one extraordinary potato. Thank you for watching The History Of. If you enjoyed this documentary, please like the video and subscribe. And tell us in the comments, what everyday food should we explore next? Because every ordinary thing has an extraordinary story.